Hello, everybody, and welcome to our second lesson in Chapter 1, which is 1.3, Part 1, New Functions from Old Functions. So basically, we're just going to be doing a bit of a review of combinations of functions and composite functions, and then also going through something called symmetry and odd and even functions, which will be new for most of you, also increasing and decreasing. So increasing and decreasing is first. These ones, you would have briefly talked about this when you did exponential functions in Math 12, and these are very intuitive. From left to right, if you read the function and it goes up, it's increasing. So the very formal way of saying this is if you have x1 and x2, so x1 is less than x2, this means you're going to read from left to right. Then the corresponding points, f of x1 and f of x2, also increase as you read left to right. Okay, so as x increases, y increases. Okay. Similarly for decreasing, if I take a look at an x1 and an x2 value reading from left to right, my corresponding f of x1 and f of x2 will decrease left to right. So as x increases, y decreases. Okay, so this is increasing. As x increases, y increases. And this one is decreasing. As x increases, y decreases. Okay. So again, fairly intuitive. If you look at the graph and it goes up, it's increasing. If it goes down, it's decreasing. Okay. So for example, this function below, okay, where is it increasing and where is it decreasing? Well, we can see as we read left to right, where we start at -4, 4, we go down up until we reach this point, -1, 1, and then we're going up again as we read left to right. So here we are decreasing and here we are increasing. Okay. So on what intervals? When we're talking about intervals, we're always talking here about x values of increasing or decreasing. So we're going to increase starting on that middle point, which is at a value of -1 up until the end point, a value of 4. And we can include both those endpoints there. And now our decreasing values, we started at the left endpoint, -4 up till the right middle point there, -1. Okay. Symmetry is our next idea. So we have three types of symmetry. Symmetry about the x-axis, meaning the x-axis sort of acts like a mirror. Symmetry about the y-axis, meaning the y-axis sort of acts like a mirror. And symmetry about the origin, meaning like if you reflected this thing diagonally across the origin, you would have a nice reflection there. So there are some points that correspond. So if I have this point xy on my positive quadrant here, and I have symmetry about the x-axis, the corresponding point should be x negative y. If we have symmetry about the y-axis and I take that point xy, this one should be symmetric across the y-axis and the corresponding point would be negative x. Why? For symmetry about the origin, okay, this one's going to have a change in x and y. The corresponding point will be negative x, negative y. Now this is going to help us a little bit with odd and even functions. An even function, by definition, is when f of negative x equals f of x, And an even function will have reflection across the y-axis or symmetry about the y-axis. So for an even function, some point xy will have a corresponding point negative xy. For an odd function, a corresponding point to xy should have a corresponding negative x, negative y. So f of negative x is equal to negative f of x. So an example would be if y equals x, or I'll put it in function notation so that it's a bit easier to understand here. If you have f of x equals x squared, if you try f of negative x, you get negative x squared, which is also x squared. So this is equal to f of x, and so therefore this is an even function. If I were to try, for example, f of x equals x cubed, f of negative x would be negative x cubed, which is the same as negative x cubed, which is negative f of x, and so this one would be odd. Let's try an example. It says determine whether the following function is even, odd, or neither. The first thing I would choose to do is determine, well, what is negative f of x? So if we are even, f of negative x should equal f of x, which is 1 over x. If we are odd, f of negative x should equal negative f of x, which would be negative 1 over x. And if it's neither, it will equal neither. Right? So this is what we're trying to determine. What does it equal? So let's try plugging in f of negative x. This gives me 1 over negative x, which is the same as negative 1 over x, which is the same as what I had here. And therefore this would be odd. Okay. Next, we're going to talk about combinations of functions. So we have different types of combinations that we would have seen in Math 12. Depending again on who your teacher was, you might have done all of these. You might have only done the harder ones that are going to be at the bottom of the next page. These are very straightforward, these ones. If you have f plus g of x, f minus g of x, f times g of x, or f over g of x, you can rewrite these all. This should be a multiplication sign in here. So you can expand that out as adding those two separate functions, subtracting, multiplying, or dividing the two separate functions. Okay. To find the domains of these, you're going to consider the domain of both. So the intersection. So you're looking for any x values that are in both domains here. Okay. So you need to consider all the domains. Okay. The only change will be if you have dividing two functions, you also must add in a new restriction that is the domain of the bottom. You have to have the bottom part of your fraction can't be 0. Okay, so let's just try a question that uses these. So if we have f of x is root x and g of x is root 9 minus x squared, we want to determine f plus g and f over g and state their domains. The first thing I would do is find the domains of each of these. That's going to make our lives a little bit easier. Okay, so your domain of this first one would be that x has to be greater than or equal to -1. Your domain of this second one, most people have a hard time with this. I would rewrite this. Okay. I would say, well, I know that this is equal to root 3 minus x and 3 plus x. Okay. My x-intercepts would be -3 and 3. The quadratic inside is like an upside down parabola because the x squared is negative. And I know that in order to square root it, I have to be square rooting positive values, which would be all these values. So therefore, my domain would be between -3 and 3. Okay. Now, if I want to determine f plus g, this is going to be root x plus 1 plus root 9 minus x squared. My domain, I have x is greater than or equal to -1 for this one, and I have x has to be between -3 and 3. Now, these are not both possible because this one says x has to be bigger than -3, but this one says bigger than -1. So I'm going to take the most restrictive of the domains. So what I'm going to say is, okay, the smallest number I can have is -1, and I would go up to 3. And the reason I'm going to choose the -1 is because if I chose -3, if you plug -3 into this root, it doesn't work. If I plug -2 into this root, it doesn't work. So you always are going to pick the more restrictive of the domains. Okay? Now, if I do f over g, this is going to give me root x plus 1 over root 9 minus x squared. So again, for domain, from the top, I have that x is greater than or equal to -1. And from the bottom now, I have -3 strictly greater than, strictly less than. My denominator cannot equal 0, so we cannot have 3 and -3 included. Again, now I'm going to take a look at both these and say, what's the smallest number I'm allowed? So from my bottom, the smallest number is -3, or just a little bit bigger than that. But from the top, the smallest I can have is -1. So again, I need to include that -1 as my smallest number, and the 3 is my biggest number. So the only difference in the two domains here is that we cannot equal 3. So this is my only difference here. If I were to do subtracting or multiplying, I would end up with this same domain I had for the adding. So the last type was composite functions. These are going to be the ones you will use the most throughout calculus. You need to be comfortable with composite functions, not necessarily finding the domains, but at least being able to rewrite them and plug one function into the other. When you find domains of these, if you are asked to do so, you must consider the domain of the inside. Write this down if you want. You need to consider the domain of the inside and of your whole final simplified function. Okay, so these did not ask us for domains, they've just asked us for the composite functions. But if you wanted to find the domains, you could. Again, you'd consider the inside function and then your final function. Okay. So for example, this first one, we are being asked for f with this little circle of g. This means that f is the outside function and the g is the inside function. Okay. So what this is asking us to find is f of g of x or f of x squared plus x because the g of x is x squared. Again, we reviewed this in the last chapter. You need to be comfortable with function notation. If you are not, you are going to have a very hard time in this course. Okay. If I want to find f of x squared plus x, this means in my function I was given, I'm going to replace an x with all of this stuff. So instead of having 4 minus x, I have 4 minus all of this, or negative x squared minus x plus 4. So if I did want to find the domain of this, I would need to consider the domain of g of x, okay, which is all real numbers, it's a parabola, and then also the domain of this answer, which is also all real numbers. So my domain for this would be all real numbers. My final one, my outside is f, my inside is also f. So this is f of x. or f of 4 minus x. So again, if I'm replacing the x with all this stuff, I'm going to have 4 minus that stuff, which gives me 4 minus 4 plus x, which gives me x. And that's it.